This is section 8.3, conic sections and nonlinear systems. As you can see there's a general form for all quadratic equations that lead us to the conic sections. And if you have it in that order, A and C are particularly important in trying to decide what kind of parabola what kind of conic section we're going to have. And I think I've been mentioning these as we go. So that's just kind of a summary of how you'll know if it's a parabola, circle, ellipse, or hyperbola. So next one, decide on the type of the conic section represented by each. All right, so let's do these one at a time. See how we get going here. X squared equals 25 plus 5y squared So having both x squared and y squared means that it's not a parabola. We do want all of the squared terms, or all the variables on the left side of the equation when it's not a parabola. So I'm going to subtract 5y squared from both sides, and then divide both sides by 25. And I can tell that this is a hyperbola now, by the way, because the coefficients of x squared and y squared have opposite signs. All right, so that's a hyperbola. We're going to do a quick sketch here, not the full-blown sketches like we did in each of the prior sections. This is just basically to kind of double check that we are getting what we think and we know how to do it. So I'll not be spending tons of time on these graphs. Okay, so I've got enough of it to go in there. Alrighty. So the center is 0, 0. The x radius is 5, so I'm going to go to the right 5 and to the left 5. The y radius is square root of 5. So square root of 5 is slightly bigger than 2, so about right there, and about right there, up and down from the center, square root of 5. And then we build our box, a rectangle. Then we draw our diagonals through that rectangle. You can tell I'm more of a hurry. Make sure we get the correct graph without worrying too much about it. Okay, so which way does it open? Well, the positive fraction has x in it, which means we're going to open into the x direction. So we go to the point that we found using our x radius value of 5 and draw the branch to the right, and likewise on the left side, branch to the left. Okay, so that's the first one. B. X squared minus 8x plus y squared plus 10y equals negative 41. Okay, this appears to be a circle because the coefficients of x squared and y squared are the same. So I'm going to complete the square, so I need to leave some space for that number that will be added to the variable terms to complete the square. So I'm just leaving a little space. And don't forget, whatever you do to one side, you have to do to the other side. All right, so the number that completes a square for for the x's is negative 4 squared is 16. So add 16 to the other side as well. And the number that completes the square for y, half of 10 is 5, 5 squared is 25. So add 25 on both sides. And then factor the trinomials that are created, x minus 4, quantity squared, plus y plus 5 quantity squared equals 25 is 31, 40. Oh, that ends up being 0. That's actually an interesting thing. If you're adding two things that are equal to 0, they either have to be opposites, which can't be true because they're both squared terms, which means they're both non-negative. Or if you add 0 to 0. And so the only way this can happen is at the single point, which means that this is a point circle. It's one of our degenerate forms. When the equation of the circle, if r squared is 0, it's a point circle. And so the coordinate of that point that makes the equation true is 4, negative 5. And the graph of that one, not that earth-shattering. It's just a point. And that point is right there. That's the only ordered pair that makes that given equation true. So that's kind of interesting. Okay, if you have a sum of two perfect squares that equals a negative number, that can't happen. That would be no graph. Just saying, so that in case that comes up, that's just a no graph situation. All right, let's do the next one. C. 4x squared minus 16x plus 9y squared plus 54y equals negative 61. Okay, this has the form of an ellipse because the coefficients of x squared and y squared are the same sign but different numbers. So for the x's, I'm going to factor off the 4 so that the coefficient of x squared is positive 1. I'm going to factor off the 9 from the y's to make the coefficient of y squared inside the parentheses equal to 1. And don't forget to leave space for the numbers that complete the square. So half of negative 4, negative 2 squared is 4. So I'm really adding 4 times 4 to the left side. So I need to add 4 times 4 on the right side. And half of 6 is 3. 3 squared is 9. I'm really adding 9 times 9 to the left side. So I need to add 9 times 9 on the right side. Okay, and then factoring. That leaves 4 times the quantity x minus 2 squared plus 9 times the quantity y plus 3 quantity squared. Let's see, 16 and 81. 20, this is 36. So I now need to divide both sides by 36 to get this into standard form for the ellipse. So when I divide both sides by 36, the 4 cancels, leaving 9 in the denominator for x, and 9 and 6 cancel, 9 and 36 cancel, leaving 4 in the denominator for y. All right, so let's sketch this graph relatively quickly. The center is at 2, negative 3. By the way, all the things I'm saying right now are things you would need to write down like we did when we introduced each of these conic sections. This is a quick, very quick graph, not done completely as I would want you to do. This is just to double check that you're able to graph and get correct answers. All right, so So from the center at 2, negative 3, I'm going to use the x radius of 3, which will take me 3 to the right and 3 to the left. And the y radius is 2, so it'll take me up 2 and down 2. And then draw an elliptical shape through those 4 points. All right. Part D. So that equation is x squared minus 6x plus 8y minus 7 equals 0. That has only x that's squared. There is no y squared term, so this is a parabola. This one's a little bit different from the other ones. We are going to complete the square, but only for x. And what you want to do here is take all of the other things that are not x to the other side of the equation. So I'm taking the y and the constant over to the other side. So completing the square, I'll need to add 9 to both sides. Factoring leads me to x minus 3 quantity squared. Combining like terms gives me negative 8y plus 16. And then to finish this, the squared variable has to be by itself on one side like it is with a coefficient of 1 like it has right now in front of that parentheses. On the other side, you're going to want this to be some number multiplied by 1y inside. So what that means is we have to factor off the negative 8 to make it a 1y inside. And so that would become negative 2 when we factor out the negative 8. All right, so let's plot this one. Excuse me. So the not the center, the vertex is at 3, 2. Since this is an x squared parabola, it either opens up or down. I am going to go ahead and write this step down just so that it's very clear where I got the value of c. So I set the coefficient of the non-squared variable, negative 8 in this case, equal to 4c, and solve for c. And so since c is negative 2, and since x squared is the variable that's squared as x, that means that we're going to move up and down that value of 2. The focus will be in the downward direction because c is negative. So that puts it right there. That's where the focus is. And going the opposite direction 2 will get us to that directrix. I'll just draw a solid line here. There's the directrix. So the other 2 points that are easy to graph and easy to find are, if you take double C, that's 4, move from the focus parallel to the directrix 4, so I'm going to go right 4 and left 4 to find 2 more points on this thing. So 1, 2, 3, 4 to the left of the focus, 1, 2, 3, 4 to the right of the focus, and those are 3 good points, the vertex and those 2 points we just found. Those are good points on this parabola, which we can then sketch to the best of our ability. Oh, you know what I haven't been doing, and I should have been writing, because it said decide on the type of conic. I said it each time, but I didn't write it. So if you want to go back in your notes and fix that, that's probably not a bad idea. So, oops, not too far. So you would need to write as an answer for A is hyperbola. That's the type of conic it is. Part B, I actually did do that. I called it a point circle. So lucked into that one, that I had done that. The next one, we would identify it as an ellipse. So okay. And then this one, of course, is a parabola. So if the directions say to determine the type of conic, you do need to write the name of the type of conic it is. All right. All right, so let's do E. 4y squared minus 16y minus 9x squared. Okay, since the signs of the coefficients of x squared and y squared are opposite, this is at least potentially a hyperbola, unless it's one of the degenerate forms. But that would be my first guess. So I'm going to need to complete the square for y. So I need to factor off the 4 so that the coefficient of the squared variable is, oops, shouldn't try to talk and write at the same time. So the coefficient of the squared variable is 1 inside the parentheses. Leave space for a number. Coefficient of x squared needs to be factored off, so factoring off negative 9. Be very careful here. That leaves minus 2x. Negative 43. Okay, so the number that completes the square for y is 4. So I'm going to need to add 4 times 4 to both sides. And the number that completes the square for y is 1. So I need to subtract 9 times 1 from both sides. This factors to be 4 times the quantity y minus 2, quantity squared, minus 9 times the quantity x minus 1 squared. Let's see, negative 43, negative 52, 16 is negative 36. You may be thinking, uh-oh, this is not good. We got that equal to a negative number, but that's okay. Think about this. You're subtracting two things. The subtraction of two things can be negative without any issues, so not to worry. So I'm going to divide both sides by negative 36 to turn that into an equals 1. And 4 goes into negative 36 negative 9 times. And then dividing the second thing by negative 36, it leaves 4, positive 4, equals 1. So this is a hyperbola. I should probably write that answer before I forget. The center of this one is at what? I'll let you think for a second about that while I'm doing this. Okay, did you think the center was at 2, 1? If you did, oops, the number with x is the x-coordinate of the center. The number with y is the y-coordinate of the center. So it's actually 1, 2. And for that reason, a lot of people, no matter what the signs in front of those fractions are, a lot of people will automatically always try to get the x fraction in front so that you don't make the mistake that some of you may have made and reverse the coordinates of the center. So 1, 2. Let's see. This is hyperbola, so I'm going to go in the x direction, the y radius 2, so right 2, left 2. I'm going to go in the y direction, 3, so up 1, 2, 3, down 1, 2, 3. Then I'm going to build my box. That uses those 4 points as the midpoints of the sides of my box. Then I'm going to draw the diagonal, or diagonals, as dotted lines. These, of course, my asymptotes. And because x is the variable in the positive fraction, I will open to the right and to the left. Oh, that doesn't look good. Let me try again. Not bad. Again, please refer to the prior section as for all the detail that you would need to provide that I skipped over, most of which I said out loud, but I didn't write it down. So kind of incomplete, but that was the point, was to identify the type of conic and then do a quick sketch just to verify that everything's all right. So I need to turn several pages here, past all of my answers that I have for myself. Okay. Now, the next thing is solving a system of equations. You may recall from prior courses how you would solve a system of equations like, I'll make one up, 2x plus 3y equals 7, and maybe 4x minus 8y equals 3. And you may have learned a technique called linear combinations. Or that's what I call it, linear combinations. And what that involves is multiplying one or both equations on both sides by a constant so that when you do that and add the two equations together, one of the variables disappears. So I'm multiplying the top equation on both sides by -2. And I'm going to leave the other equation alone. I'm not actually going to finish this. This is just to get you the idea of how we did this in a college algebra setting. Then we add those two equations. The x's, of course, become 0x, which I won't write down, and those add to be -14y, and equals -11. Then you divide both sides by -14. Yuck, I made up a really nasty one. Oh well. And that's the y-coordinate of the point where those two graphs intersect. And remember, that's what you're finding when you solve the system, is any points of intersection. So we would then go back to one of the equations and substitute 11/14 in for y and solve for x, or we could do linear combinations a second time, but this time target removing the y. So you might multiply the top equation by 8 and the bottom equation by 3 to eliminate y and solve for x. So at any rate, I made up a nasty one, so I'm not going to finish it. You're probably thankful with that fraction in there. But the point of intersection would be something 11/14. That's what it would be, whatever that actually ends up equaling. And so our solution set is going to consist of all ordered pairs where those two graphs coincide. And so for two lines, that can only be 1 point, or no points if the two lines are parallel, or infinitely many points if they're the same line. Okay, that's not going to be a big issue in this section. Most of the problems that you're going to have here involve at least 1 point in the solution set. So, oh, I forgot to do something. I'll do it off to the side really quickly. Let's say, for example, like in this problem, you have a circle and a hyperbola. So, could those intersect at exactly 1 point? If it looked like this, for example, yes, that could be one solution. Could they intersect in 2 points? And there are several ways this could happen. I'm just going to draw one of them. Okay, that's 2 points of intersection. Could you get 3 points of intersection? We're just talking about can you. Oops, that's not a very circular circle, but pretend. Yes, you could get 3. Could you get 4? Yes, you could. Could you get 5? The answer to that is no. Oh, and what I should have probably started with, is it possible that you'll get no points of intersection? Yes, that is indeed possible as well. So you have anywhere from no points of intersection, which means your solution set would be the empty set if you get no solutions, or your solution set can contain anywhere from 1 to 4 ordered pairs of points of intersection. So anyway, coming back to this problem, it looks like I could just simply add these two equations as they are, because the y squared coefficients are already opposites. So if I add those, I'll get 3x squared equals 12. So x squared equals 4. And this is something you have to be very careful about. You'll miss half of the answers if you don't remember that when you take the square root of both sides, you need to put in a plus or minus. Okay. So to find out what y will be, start with one of the two x values that's allowed. Let's start with 2. Using the top equation, 2 squared is 4, plus y squared is 4. So y squared is 0, so y is 0. In the other case, when x is negative 2, using the first equation again, negative 2 squared is 4. And that's actually the same equation as we just had. So I'm going to skip the work and just jump to the conclusion that that's 0. So this solution set contains the ordered pair positive 2, comma 0, and negative 2, comma 0. And if you wanted to, you could sketch those two graphs and determine that they actually are intersecting each other at those 2 points. All right. Now let's work another system. Solve the system. X squared plus 3xy. Oh boy, we've never had one of those with an xy term in it. So you're not graphing this one because you don't know how. So you can't really check this one by graphing. The xy term is a possibility that we don't encounter in pre-calculus much. And the main reason for that is that what that does is it can change the type of conic section you're getting to a different one. And it can also have a rotational effect. And so you can have a parabola that instead of opening up, down, left, or right, opens at some strange angle like this. And we're not dealing with those at all in this course, so not to worry. So I'm looking at the coefficients, and I notice that the x squared and y squared coefficients are identical. So if I were to multiply the bottom equation by 1 on both sides, those coefficients for both x squared and y squared would become opposites. Make sure you multiply everything by -1. That's a pretty common mistake that people will make, is to, you get over here and you forget and you write +6 instead of -6. The other equation I'm just leaving alone. It's x squared plus 3xy plus y squared equals 22. So when I add those two equations together, I get 4xy equals 16. So that means xy is equal to 4. And one thing you can do here is another technique of solving systems is you can solve this for one of the two variables. It doesn't matter which one. I'll solve for y by dividing both sides by x. And then you can substitute for y in either of those two equations with 4 over x. So let's go with the second equation. So that will be x squared minus x times 4 over x plus 4 over x squared equals 6. Simplifying, I get x squared minus 4 plus 16 over x squared. You may remember from an algebra class in the past that if you have fractions in the equation, you can eliminate those fractions from the equation by finding the common denominator of all of those fractions and multiply both sides by that common denominator. So if I multiply both sides by x squared, that's going to clear out the denominators of any fractions I have. So this will become x to the 4th minus 4x squared plus 16, which equals 6x squared. So subtracting, because remember in a case like this you want to set a polynomial equal to 0 and see if it will factor. Okay, so subtracting 6x squared from both sides gives me that trinomial. I sure hope it factors, because if it doesn't, we have to go to the quadratic formula. So to get x to the 4th, I could multiply x squared by x squared. And I want to think of factors of positive 16 that would add to be negative 10. I think negative 2 and negative 8 fit the bill. And so this means that x squared is either equal to 2 or x squared is equal to 8. So in the first case, that means that x would be plus or minus the square root of 2. And in the second case, x would be plus or minus the square root of 8, which simplifies to be 2 square roots of 2. Okay. So the best equation you can use to go forward from here to find y is this one right here. That has a solution for y if you know x. So when x is the square root of 2, y is 4 over the square root of 2, which is 4 square roots of 2 over 2, which is 2 square roots of 2. When x is negative square root of 2, y is 4 divided by negative square root of 2, and that will simplify like we did the other one into negative 2 square roots of 2. When x is 2 square roots of 2, y will be 4 divided by 2 square roots of 2, which simplifies to be 2 divided by the square root of 2, which is 2 square roots of 2 over 2, which is the square root of 2. When x is negative 2 square roots of 2, y is 4 divided by negative 2 square roots of 2, which ends up simplifying to be negative square root of 2. So our solution set contains the ordered pairs square root of 2, comma 2 square roots of 2, comma negative square root of 2, comma negative 2 square roots of 2, comma 2 square roots of 2, comma square root of 2, and negative 2 square roots of 2, comma negative square root of 2. Okay. Now the next example deals with graphing the solution set of a system. Now if you have of inequalities, excuse me, I didn't finish my thought, a system of inequalities, remember that involves shading. And we can't write a solution set of all the ordered pairs because there will usually be infinitely many of them. So that's why we have to graph. A lot of times in this type of problem, they're going to give it to you in a nice form so that the graphing part will not be the challenge as far as graphing the figures that are involved in the problem. So notice this is already in a nice form for an ellipse, and then the other one is in a nice form for a hyperbola. All right. So, and in this, I would not ask you to write out all of the pieces like center, x radius, y radius, and all that, unless you want to. You certainly can. But when you're doing a system and you're having to graph two sets of things, I'm perfectly fine with your being able to just know how to graph it and get the right graph pretty quickly. I will be interested to see how many of you actually still need to write stuff down, because I find that I sometimes have to, especially if it's a really difficult one. But this one I think is not going to be that challenging, so let's just go for it. All right, so the first one is an ellipse centered at 0, 0. The x radius is 5. 1, 2, 3, 4, 5. The y radius is 3. And because that says or equal to, that means the boundary line of equality, the ellipse itself, is included in any solution that we might get. So we're going to draw this as a nice ellipse like normal. The difference would be if that were just less than, we would be drawing a dotted boundary line for this ellipse because it would not be included. I think most of these that you will encounter, they're included. So you go ahead and draw the figure as is. So this is the ellipse. Now the hyperbola centered at 0, 0 has an x radius of 2 and a y radius of 3. Then I'm going to draw the box that uses those 4 points as the midpoints of each side. I can tell I didn't draw a perfect ellipse. Hopefully you'll be able to forgive me on that. Then draw the asymptote, which is the diagonal of the box. Preferably you'll use a straight edge, which is not what I'm using. Try and do it free form, which is dangerous. And satisfying though when it works out okay. Alright, and then because it's or equal to, we'll include the solid boundary, and since x is the fraction, x is the variable in the positive fraction, this will open to the left and to the right, so into the x direction. Those don't look very good. Let's see if I can do better over here. Yeah, these look better. So pretend like I did this kind of graph on the other side. That looks a lot prettier than my left side. All right, so that's this graph. Now, the set of points that make this inequality true, we're going to find all of the points that make it true. So let's start with the ellipse. That ellipse separates the plane into two regions, what's inside the ellipse versus what's outside. And so what I'm going to do is I'm going to test any point on, let's say, the inside that I want. And if that makes the inequality true, then we'll be shading inside of the ellipse. If that point makes the inequality false, we'll be shading outside of the ellipse. So if I try 0, 0, which is a really good point, the center is almost always a good one to use because it simplifies arithmetically very nicely. So 0 plus 0 is what that would be, is equal to 0. The question is that less than or equal to 1, true or false? Well, that's true, so that means we're going to be shading inside of the ellipse. So I'm going to write a couple little arrows here to indicate to me that I'm shading inside. I'll erase this in a second, but if it had been outside, I would have done arrows like that. Because we have two things to worry about, you don't want to shade quite yet. You want to wait until you know exactly where you're going to be shading. All right, so now for the second one. Center is 0, 0, so I'm going to use 0, 0. So substituting in 0 for both x and y. 0 minus 0 is 0. The question is that greater than or equal to 1? Well, that's false, which means we're not going to be shading the region between the two branches, which is where the center is located. We're instead going to be shading everything to the left and right of the branches. Okay, so where do the two shadings intersect? Because when you solve a system, both have to be true. So it has to be both beyond, to the right of the hyperbola branch on the right, and inside the ellipse. So that indicates that it will be this region. So just shade that. A few lines like that's sufficient. And on the other side, to the left of the hyperbola, but yet still inside of the ellipse. That would look like that. So that shaded region is the set of points that makes that system of inequalities true. All right, that ends the lesson. I'll see you later.